Hello and welcome to the Maths 2 component of the online BSc program on data science and programming. This video is about the Hessian matrix and local extrema for f, x, y, z. In the previous video, we have seen the Hessian test to classify critical points for the function f, x, y. In this video, we will see the same or an analogous test for f, x, y, z. So, as you can see that as your number of variables increases, the test sort of becomes a bit harder, which is why we have these separate videos. Now, one can make sense of all this in terms of linear algebra for the Hessian matrix for n variables, and in particular if we allow ourselves the notions of eigenvalues, which you will study later in your machine learning course. And also use these ideas of diagonalization and using orthogonal matrices. So, we did this when we did similarity and equivalence of matrices. Using all those ideas, we can formulate a general test for n variables, but in the interest of time and functionality as far as this course is concerned, I am not doing this for general variables. Although we have developed some of the linear algebra already required for this, but we will need a little bit more. So, I am restricting myself to 3 variables, and this will be enough probably for most of the problems that you will come across. Okay. So, let us recall what is the Hessian test for a function of 2 variables. So, if you have a function defined on the domain D in R2 and A is a critical point such that the first and second order partial derivatives are continuous in an open ball around A, then there is something called the Hessian test, which means that you compute the Hessian matrix of the function f and evaluate it at the point A. That gives you a 2 by 2 matrix. You compute its determinant and the value of the 1 1 term. If that determinant is positive and the 1 1 term is also positive, then the point is a local minimum. If the determinant is positive and the 1 1th term, meaning the fxx at a tilde is negative, then it is a local maximum. If the determinant is negative, it is a saddle point, and if the determinant is 0, which is called the degenerate case. So, the previous 3 are called the non-degenerate cases, which means that the determinant is non-zero. But in the degenerate case, which is to say the Hessian determinant is 0, this test is inconclusive. So, that is really the bad case, that is the case we want to avoid, because that means that the test does not tell us anything. Okay. So, we saw some examples of this test. We also saw that it told us the answer in some surprising cases, whereas in some cases where it was obvious what the answer should be, it turned out to be inconclusive. So, the test has it comes with it is a double-edged test. Sometimes it will work in situations where you really do not know what is happening, and sometimes it will not work even though you absolutely know what is happening, right. So, we will see something similar for the Hessian test in 3 variables. I am not going to do as many examples here, because we already know the phenomenon that are taking place, namely that it can work sometimes in spite of the fact that we have no clue of what is happening, and it may not work at all despite us knowing what is happening. So, let us see what the test is. So, again this is a function, f is a function defined on a domain D in 3 variables. Suppose A is a critical point and the first and second partial derivatives are continuous in an open ball around a tilde. I will remind you that now there are 9 second order partial derivatives: fxx, fxy, fxz, fyx, fyy, fyz, and then fzx, fzy and fzz. Of course, thanks to Clairaut's theorem, we know that we can interchange the order. So, fxy and fxyx are the same, fxz and fzx are the same, and fyz and fzy are the same. So, effectively there are 6 partial derivatives. So, this is a fairly long computation if we want to compute this. And then the Hessian matrix is where we put these second order partial derivatives into a 3 by 3 matrix. Remember, it is a 3 by 3 matrix now, because you have 3 variables. And then the test tells us that if the following things happen, then we can classify the critical points. So, if the term f(x(x) is positive, the term f(x(x) times f(y(y) minus f squared xy, which was the determinant that we used in the 2 by 2 case, if that at A tilde is positive, and if the determinant of the entire Hessian matrix is positive, then A is a local minimum. If on the other hand the f(x(x) is negative, the second term f(x(x) f(y(y) minus f squared xy at A tilde is positive and the determinant is negative. So, this is alternating sign, then A tilde is a local maximum. If the determinant is non-zero and neither of cases 1 or 2 occur, then A tilde is a saddle point. So, that means in these two, the first two cases we have local minimum or local maximum, and in all the other non-degenerate cases, meaning where the determinant is non-zero, it is a saddle point, and if the determinant is 0, which means it is a degenerate situation, then the test is inconclusive. Okay. So, this is the Hessian test in the 3 variable situation. This is getting slightly complicated, as you can see, and which is why I am not describing this in the general n by n setup. It actually has an easy description, but for that we need to know what are eigenvalues. Okay. So, let us understand these terms better. So, the terms involved in the test are f(x(x), f(x(x), f(y(y) minus f squared xy at A tilde and determinant of this matrix at A tilde. So, what are these terms? Let us write down the matrix. So, here is the matrix f(x(x), f(x)y, f(x)z. So, I am not really caring now about the order, whether it is f(x)y or f(y)x, because of Clairut's theorem, f(y)y, f(y)z, and then f(x)z, f(y)z, and then f(z)z. And let me draw this like this. Okay. So, this is our Hessian matrix. So, this is a Hessian matrix, and maybe let us do this at A tilde. So, in that case I have to evaluate all these at A tilde. Right. So, once I evaluate, these are numbers, right? These are all numbers. Okay. And what do these terms correspond to? So, f(x(x) at A tilde corresponds to this term here. So, it is the 1/1th term or the 1 by 1 matrix in the top left corner. Okay. This second term, so the second term here, this term, so this term corresponds to the determinant of the 2 by 2 matrix in the top left corner, and the third term, which is the determinant of HF of A tilde, corresponds to the determinant of the entire matrix. So, what we are doing is we are taking the determinants of the top left corner successively larger. So, the 1 by 1, 2 by 2, 3 by 3, and in fact, we can generalize this to n by n. Only thing is those signs we have to be careful of how they work. And what we are saying is that if that top left corner, if the sign is like this, if it is plus, plus and plus, so which means that this is the 1 by 1, 2 by 2, 3 by 3. If it is plus, plus and plus, that means they are greater than 0, greater than 0 and greater than 0, then this is a local minimum. If it is a minus, plus and a minus, note the alternating sign. This is very, very important. This is where students often make mistakes. If it is a minus, plus and a minus, it is a local maximum. And in all the other cases where this is not 0, where determinant is not 0, all other non-degenerate cases, by which we mean that the determinant is not 0, this is a saddle point. And if it is the degenerate case, which means the determinant is 0, this we can't really say. So, this is the really bad part, right. So, this is what it is saying. So, what you have to keep track of is you have to compute 3 successive determinants. The first one is a 1 by 1 determinant. So, that really there is nothing to say. The second one is a 2 by 2 determinant, and the third one is a 3 by 3 determinant. So, in practice you do it the other way, because you want to check that the determinant of the entire matrix first is non-zero. If the determinant of the entire matrix is 0, then you stop the test right there. So, what you do is your testing should start in the opposite direction. So, you do your testing in this direction. First you test this, then you test this, and then you test this, right. So, first you test the entire matrix, what is the determinant, whether it is positive or negative or 0. If it is 0, end of story. If it is positive or negative, then you test for the 2 by 2. If the 2 by 2 by chance happens to be negative, stop right there, because as you can see here you want it to be positive. So, then it is a saddle point. If it is positive, then you check for the 1 by 1, right. That's the way to go. Okay. So, let us do a couple of examples. So, these are again sort of our test examples to remember how the rules work. So, the functions are also very familiar here. So, let us first do x square plus y square plus z square. Clearly, this is a non-negative function, and the only place it 0 is the point 0 0 0. So, this is 0 0 0 is a local minimum, and in fact it is a global minimum, and in particular it is a local minimum. So, hopefully the Hessian test will tell us that. So, gradient is 2x 2y 2z. Hessian is well, you can compute this. Now, I am doing this rather fast. 2 0 0 0 2 0 and 0 0 2. Let us compute the various things that we have to compute. So, at 0 0, so the critical point is 0 0 0, and so the Hessian at 0 0 0 is the same thing, and so we should compute the determinants of all the top left matrices of decreasing size. So, the determinant of the entire thing is 8, which is positive. Actually, you can see all of them are going to be positive, but I will just determinant of the second one is that 2 0 0 2, that is 4 positive. So, which matrix are we looking at? It is this matrix here, and then determinant of the first meaning the entry in the 1 1 1th place, that is this entry here, right. So, that entry is positive. So, f x x at 0 0 0. So, therefore, this is a local 0 0 0 is a local minimum, and that is exactly what we had in our case 1, right. So, this is how you can remember case 1. Similarly, if you take minus x squared minus y squared minus z squared by the same argument, it is always a non-positive function. The only place at 0 is the point 0 0 0. It is a global maximum, and so hopefully the Hessian test picks that out. So, I am going to sort of do this really fast. Gradient is minus 2x minus 2y minus 2z. The Hessian matrix now you can write down is minus 2 0 0 0 minus 2 0 0 0 minus 2. Critical point is clearly 0 0 0 0. So, this is the Hessian also at that critical point, and now let us see what the signs are. So, the determinant is of the entire matrix is minus 2 times minus 2 times minus 2. It is a diagonal matrix. This is negative. So, we have a minus sign. The determinant of the 2 by 2, that is minus 2 0 0 minus 2, that is minus 2 times minus 2, it is 4, it is positive, and then the 1th entry is minus 2, which is negative. So, the signs here are, this is the important part, what are the signs? The signs are minus, plus, minus, and that tells us this is a local maximum, and indeed this is what we already know, and so this is how you can keep this in mind. Similarly, if you take x squared minus y squared plus z squared, you will get it is a saddle point. So, I will just write down the Hessian and you can do the checking. So, the Hessian is going to be 2 0 0 0 minus 2 0 0 0 2. So, the signs you are going to get are determinant of the entire. So, the critical point is 0 0 0 and the signs you are going to get are so minus 8 2 by 2 is 2 0 0 minus 2, which is minus 4, and already you can stop right here because Hessian is the Hessian determinant is non-zero and the signs are not corresponding to either alternating or plus plus plus. So, you can stop right here, but just to finish it at 0 0 0, this is 2, which is positive. So, this is a saddle point, and indeed we already know this because of, well, you can check that along certain axis it is a local maximum, along certain axis it is a local minimum. Okay. And finally, if you take x to the power 4 plus y to the power 4 plus z to the power 4, what happens? The gradient is 4x cube, 4y cube, 4z cube. Critical point is clearly 0 0 0 by equating this to 0, and the Hessian you can compute from here is 12x squared 0 0 0 12y squared 0 and 0 0 12 z squared. And what happens at the point? So, at the point 0 0 0, this is the 0 matrix, right, and as a result it is the degenerate case, we can't say anything. So, this is inconclusive as far as the Hessian test is concerned. On the other hand, we already know that x to the power 4 plus y to the power 4 plus z to the power 4 is always non-negative. It is the fourth power, they will always be non-negative, and the only point where it takes the value 0 is the point 0 0 0. So, this is in fact a global minimum, so in particular a local minimum. So, in spite of the fact that we easily know that this is a global minimum, the test is inconclusive. So, these are the 4 prototype examples you should keep in mind to in case you forget the tests. So, these will tell you. Okay, let us do a couple of examples of computing this. So, here is f x y z is x y plus y z plus z x. So, gradient f, we have actually computed the gradient and the Hessian. So, the gradient here is y plus z, z plus x, x plus y. So, you equate this to 0. So, then we get these 3 equations, y plus z is 0, z plus x is 0, x plus y is 0. So, that tells us that x is minus y, and that also tells us that x is z. That is what we get from equation 1 and 3, but equation 2 tells us that x is minus z. So, the only way this can happen is if x is equal to y is equal to z is equal to 0, right. So, the only solutions here are x is equal to y is equal to z is equal to 0. So, the critical point is 0 0 0, and what happens to the Hessian matrix? So, what is the Hessian? So, if we write down the Hessian, which we have actually done before, we get 0 1 1 1 0 1 and 1 1 0. So, this is in particular the Hessian at 0 0 0, and what happens? So, let us do our test. So, first, what is the determinant of the Hessian matrix? So, this is okay. So, if we do our determinants, this is 0 times determinant of the 1 by 1 1 minor minus 1 times determinant of 1 1 1 0 plus 1 times determinant of 1 0 1 1. So, if we compute this, this is 1 plus 1, which is 2. So, this is positive. Okay, so at least it is non-zero. So, we are in business. This test is going to be conclusive. So, now we take the 2 by 2 left top left matrix, calculate its determinant 0 1 1 0. This is minus 1, negative, and well, as soon as we know it is negative, this does not correspond to case 1 or case 2. So, this means it is a saddle point. So, therefore, 0 0 0 is a saddle point, and I will encourage you to check why it is a saddle point. So, find a sequence of points which go to 0 0 0, for which 0 0 0 on that curve it is it's a minimum value, and find some other curve on which it is a maximum value. 0 0 0 is a point of maximum. Okay. So, I hope it is clear how we are using this test, right. So, let us do this final example of x to the power 4 plus y to the power 4 plus z to the power 4 plus x y z. I want to do this example just to show you that sometimes these calculations do become rather difficult, doable, but difficult. So, what is the gradient? So, the gradient is 4x cube plus yz, 4y cube plus xz, 4z cube plus xy. Let us set this to 0. So, equating to 0, and we will have to really work this out. We get, so you have 3 equations. 4x cube plus yz is 4y cube plus xz is 4z cube plus xy is 0. Okay. So, now we have to solve these 3 equations, and note that these are not linear equations. So, our linear algebra will not really help us over here. So, we have to sort of see this and solve this by brute force, and also using the fact that they have a very nice form. So, here's where your comfort with equations or algebra in general will kick in. Okay. So, case 1 is there is one solution staring us in the face, namely where x is equal to y is equal to z is equal to 0. And it is very important to note that once one of them is 0, all the others are 0. For example, if x is 0, then you can put that into the equation 4y cube plus xz is 0, and that will give you that 4y cube is 0, and that will say that y is 0, and you can put it into the equation 4z cube plus xy is 0, and that will say that z is 0. So, by symmetry, if one of them is 0, all of them are 0, right. So, that is case 1. The other case is where none of them are 0. So, all are non-zero, all are not non-zero. Yeah. So, none of them are 0. So, in that case, what we can do is we can multiply each of our equations suitably. So, the first equation we can multiply by x, and we can say that 4x to the power 4 plus xyz is 0, which means 4x to the power 4 is minus xyz. But I can do the same thing for the second equation by multiplying it by y, and I can say that 4y to the power 4 plus xyz is 0, which is saying that 4y to the power 4 is minus xyz, and by symmetry we will also get that this is 4z to the power 4. Okay. So, what that means is 4 x to the power 4 is 4y to the power 4 is 4z to the power 4. So, x to the power 4 is y to the power 4 is z to the power 4, and they are not all 0. Fine. And now if we take the fourth root, what that will tell us is that x is plus or minus y, and again which is plus or minus z. And now we can so now we can substitute this into our equations. So, substitute in 4x cube plus yz is 0. So, if you substitute this, what you are going to get is 4x cube plus x squared is 0, and since x is non-zero, we can cancel x squared on both sides, and what we will get is x is either you get this or 4x cube minus x squared is 0, and then what we will get is x is 1 by 4 or x is minus 1 by 4. And then so again for y and z also you will get these three. Of course, all possible solutions may not be correct, because they have to satisfy these equations over here. So, then you have to back check for what values these are satisfied, and if you do that, you will get your critical points as 0 0 0, which was case 1, and then from here we will get 1 minus 1 by 4 comma 1 by 4 comma 1 by 4, 1 by 4 comma minus 1 by 4 comma 1 by 4, and 1 by 4 comma 1 by 4 comma minus 1 by 4, and finally minus 1 by 4 comma minus 1 by 4 comma minus 1 by 4. So, these are the 5 critical points that you will get, and now we have to check the nature of these critical points. So, let us see what is the Hessian. So, if you compute the Hessian, what you are going to get is 12 x squared z y, then z 12 y squared x, and then y 12 z y x 12 z squared. Okay, fine. So, now we have to evaluate this Hessian at all these various points and check what happens. So, already you can see that for 0 0 0 this is inconclusive. So, we can't really say anything about 0 0 0. So, 0 0 0 it is inconclusive. And again I will encourage you to check what happens at 0 0 0. My claim is that this should probably be a saddle point. What happens at the other points? And by symmetry, for these three at least we should get the same thing, and then we have to check minus 1 by 4 minus 1 by 4 minus 1 by 4. So, let us check minus 1 by 4 comma 1 by 4 comma 1 by 4. So, in this case the Hessian is let us write that down, 3 by 4 1 by 4 1 by 4 1 by 4 3 by 4 minus 1 by 4, and then 1 by 4 minus 1 by 4 3 by 4. Okay, now you can use our good old determinants and check what we are getting. So, notice here that there are constants in this. So, you can pull out the constant. So, this matrix is 1 by 4 multiplied by the matrix which consists of integers, if that makes your computation easier. And remember that when you take determinant, since it is a 3 by 3 matrix, that constant will be to the power 3. So, if you do that, the determinant of the entire thing is maybe I will not do the actual computation, and I will just say that this is positive. You can see that is the case because on the diagonal the terms are rather large. So, this is positive, and then for the 2 by 2 again this is positive, and the 1 by 1 is again positive. So, this is a plus 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 situation, that means this is a local. So, this is all these three are local minima, right. And finally, we have the last point, and again actually the same thing happens. So, in this case you get 3 by 4, but all the off diagonal entries are minus 1 by 4. So, So, 3 by 4 in the diagonal and minus 1 by 4 everywhere else. Okay. And if you compute the determinants, again you are going to get plus plus plus, which means this is also a local minimum. Okay. So, once again what you will find here is that for the points where it is kind of not so clear how the function behaves, the Hessian test is telling us something, whereas for 0 0 0 it is comparatively easier to see what is happening, because the function value there is 0 and you can try to sort of understand from which side do I come and along which curve do I come in order to get local maxima, local minima, etc. So, that it behaves like a saddle point. So, the conclusion here is that again the Hessian test is kind of the behavior is kind of surprising. Sometimes for things that you may understand relatively better, it gives you inconclusive results, but for things that you may not understand relatively less clearly, it gives you results. Now, of course, we have not gone into proofs of the Hessian test, and maybe that's a separate topic in itself. So, we will not go there. There is we can extend this, as I said, for the n by n case, but we won't do that in this course. So, the main theme of this video was that we now have a Hessian test analogous to the second derivative test for 3 variables. Thank you.